In a materials lab in China, researchers took strips of ordinary bamboo, the same fast-growing grass that covers millions of hectares of Chinese hillsides, and dropped them into a chemical bath that dissolved away part of what was holding the plant together. What came out looked ruined, soft, pale, floppy, like a wet noodle you could bend around your finger. Then they put it into a hot press and squeezed it flat, and the material that came out the other side had a strength-to-weight ratio, according to the published research, higher than most structural steel. No trees were cut. No decades of waiting for a forest to mature, just a grass that regrows on its own in 4 to 5 years. If this process ever scales the way its developers hope, the wood in your floor, your furniture, your door frames, the beams holding up your roof could stop being the obvious default it has been for the last several thousand years. Stay with me, because by the end of this video, you'll understand exactly what these researchers removed from the bamboo, and why removing it made it stronger, why the technology still isn't sitting in your local hardware store, and why the biggest obstacle standing in its way has almost nothing to do with the science. This is one of those stories where the physics is already settled, and the paperwork is what's holding everything up. Take a second and look around the room you're in right now. Count the wood, not just the obvious pieces, the table, the chair, the shelf. Look at the door, the frame around the door, the skirting boards, the floor under your feet, or the subfloor under the tile. If you're in a house in North America, Europe, Japan, or Australia, there is a very good chance that the entire skeleton of the structure you're sitting inside is wood, hidden behind plaster, holding up everything above you. Wood is so completely woven into human life that we stopped seeing it as a technology at all. It's just the background material of civilization, and the way we get it has barely changed in principle since the first person sharpened a stone axe. Find a tree, wait for it to be big enough. Cut it down, saw it into rectangles. Everything we've invented since, the chainsaw, the sawmill, the kiln, plywood, particle board, glue laminated beams, has been an improvement on that one basic transaction. We take a slow-growing organism, we kill it, and we cut it into shapes. The scale of that transaction is genuinely difficult to picture. According to the Food and Agriculture Organization of the United Nations, global wood production sits at roughly 4 billion cubic meters a year, and their most recent State of the World's Forests assessment recorded industrial roundwood removals at just over 2 billion cubic meters, a record volume. About half of everything harvested globally is burned for fuel. The other half becomes lumber, panels, and pulp. The same body's projections suggest global demand for roundwood could rise substantially by the middle of this century, driven largely by construction and packaging in a world that keeps adding buildings. And here is the part that most people never sit with. The supply side of that equation runs on a completely different clock than the demand side. A commercially useful softwood might take 30 to 40 years. A tropical hardwood, the kind that ends up in furniture and flooring, commonly takes 50 to 80 years to mature, and in some species considerably longer. So every plank you've ever bought represents a piece of time that somebody either waited for or took from a forest that wasn't going to grow back on any timescale that matters to you. We built an entire industrial civilization on a material whose production cycle is measured in human lifetimes. That mismatch is the actual problem. Not that wood is bad, wood is remarkable, but that we want it faster than it grows. To understand why bamboo suddenly matters here, you need to understand what wood actually is at the level most of us never think about. Wood is not a solid the way metal is a solid. Wood is a bundle of tubes. Under a microscope, a piece of timber looks like a honeycomb of long, hollow cells, mostly running in one direction, up and down the trunk, because that's the direction a tree needs to move water and resist wind. Those cell walls are built mainly out of cellulose, which is an extraordinarily strong natural polymer arranged in long, thin fibrils, and those fibrils are the reason wood can hold up a building at all. Cellulose, gram for gram, is genuinely impressive stuff, but the cellulose doesn't work alone. It's embedded in a matrix of two other substances, hemicellulose and lignin. Think of lignin as the glue and stiffener. It's what makes a tree rigid enough to stand up instead of flopping over like a vine, and it's what makes wood waterproof enough to survive rain. Lignin is the reason a tree is a tree. Here's the catch, and it took material scientists a long time to fully appreciate it. That same lignin is also what limits the material. Because the strong cellulose fibrils are locked inside a softer, weaker matrix and separated by air-filled cavities, only a fraction of the wood's theoretical strength is ever actually available to you. The strong part is diluted by the weak part. On top of that, Every piece of natural timber carries the biography of the tree it came from. Knots where branches grew, grain that curves, density that varies from the center outward and from one growing season to the next. Which is exactly why engineers have historically been so conservative with wood. You have to design for the worst plank in the batch, not the best one. Long-thangle limitation, strong fibers trapped in a weak, airy matrix, is the door that a whole generation of materials researchers walked through, and bamboo turned out to be the ideal thing to walk through it with. Bamboo is not a tree, it's a grass, and that distinction is the entire economic argument. A tree grows by adding rings outward for decades. Bamboo shoots up from an underground rhizome network and reaches its full height in a matter of weeks. Research published on Moso bamboo, the workhorse species of Chinese industry, has documented culms completing essentially all of their height growth in around 40 days, with peak growth rates recorded at over a meter in a single day. The stem then spends the next few years thickening its cell walls, and after roughly 4 to 5 years, it's mechanically mature and ready to cut. And because the rhizome underground stays alive when you harvest the pole above it, the plant isn't killed. Managed bamboo stands are typically harvested at around a fifth to a quarter of the poles per year, indefinitely, without the stand shrinking. Compare that to 50 to 80 years for a tropical hardwood, and you can see why researchers kept coming back to it. For most of history, though, that speed came with a penalty. Natural bamboo is hollow, tapered, round, and wildly inconsistent from one culm to the next. It's brilliant scaffolding, and it's terrible engineering lumber because an engineer can't calculate with a material whose properties change every meter. Structural design is built on predictability, and raw bamboo doesn't offer any. So the question Chinese and international research teams started asking around a decade ago wasn't how do we make bamboo bigger or straighter? It was more radical than that. What if you took bamboo apart at the chemical level, threw away the part that was holding it back, and rebuilt it into something the plant never was? Here's the simple version of what that actually looks like. Imagine a thick sponge, the kind full of air pockets, and imagine that running through that sponge are thousands of incredibly strong threads, all pointing the same direction. The threads are the strong part. The sponge material around them is the weak part, and the air pockets are just empty space doing nothing at all. Now imagine you could dissolve away a portion of the spongy filler without damaging the threads, and then compress what's left flat, so hard that all the air is squeezed out and the threads get pushed into direct contact with each other. You haven't added anything. You've just deleted the weakness and closed the gaps. That's the whole idea, and in material science it's called delignification, followed by densification. The chemistry is more elegant than it sounds. Bamboo, by composition, is roughly 45% cellulose, around a quarter hemicellulose, and around a quarter lignin, according to figures published by City University of Hong Kong, one of the institutions leading this work. Researchers soak bamboo strips in an alkaline solution which selectively strips out a controlled portion of the lignin and hemicellulose, the sponge, while leaving the cellulose fibrils, the threads, intact. What's left is a soft, porous white scaffold. Then it goes into a hot press. Under heat and pressure, the collapsed cell walls fold in on each other, the empty channels close, and the cellulose fibrils are forced into alignment and pressed tightly together. At that microscopic distance, hydrogen bonds form between the fibrils, millions of tiny chemical handshakes, and the whole thing locks into a dense, uniform solid. The numbers coming out of this work are what made the field pay attention. In a study published in the journal Advanced Materials in 2020, a team reported that processing natural bamboo this way, partial removal of lignin and hemicellulose, followed by hot pressing, produced a bulk structural material with a tensile strength of approximately 1 gigapascal and a specific strength, meaning strength relative to weight, of 777 megapascals per cubic centimeter per gram. That figure sits above a great many conventional structural materials. Different groups have taken different routes to the same destination. In a paper published in ACS Applied Materials and Interfaces, researchers described a variant they called bamboo steel, made by removing lignin and hemicellulose, freeze-drying the scaffold, infiltrating it with epoxy resin, and then densifying it. According to that study, the resulting material reached a tensile strength of just over 400 megapascals and a flexural strength of around 514, with a specific tensile strength that the authors reported as exceeding that of conventional high specific strength steel. Another team, publishing in the journal Green Chemistry, added a mineralization step, growing calcium carbonate inside the structure alongside a phenolic resin, and reported not only high tensile and flexural strength, but a substantial reduction in heat release and smoke production compared with natural bamboo, which matters enormously for a building material. And then there's the version that has actually left the laboratory. Researchers at City University of Hong Kong developed and patented a densified bamboo material commercialized under the name Super Bamboo through a startup co-founded in 2021 by Professor Lu Yang, Dr. Fan Rong, and a colleague who became the company's chief executive. According to the university, the material is around 3 times stronger than conventional engineered bamboo, with a strength-to-weight ratio described by the team's materials researcher as 350 megapascals per gram per cubic centimeter. It holds patents in both the United States and Hong Kong, and it won a gold medal at the Invention's Geneva Evaluation Days in 2021. What makes that particular version interesting isn't only the strength figure, it's what's missing from it. Conventional engineered bamboo and engineered wood products, plywood, particle board, laminated beams, are held together by adhesives, and many of those adhesives are formaldehyde-based. That's why new furniture smells the way it does, and it's why regulators in the United States and Europe have specific emissions standards for wood panels. The team behind Super Bamboo states that their process requires no glue at all. The bonding comes from the material itself, from those hydrogen bonds forming between compressed cellulose fibrils. If that holds up at industrial scale, you'd be looking at a structural material that's stronger than the timber it replaces, lighter than the steel it competes with, emits no formaldehyde, and is biodegradable at the end of its life. Quick question for you before we go further, and I'm actually curious how this splits. If a bamboo-based structural panel arrived at your local building supplier tomorrow, stronger than the equivalent timber, no formaldehyde, same price, would you use it in your own home? Or would you want to see 20 years of buildings standing before you trusted it? Drop your answer in the comments. I read them. And if you enjoy videos that dig into how materials actually work rather than just announcing that something is the future, consider subscribing. It genuinely helps this channel keep making them. Now, the honest part. The part these stories usually skip. If this material is as good as the papers say, why isn't it in your house? The answer has 3 layers, and only the first one is about science. The first barrier is cost and throughput. Every one of these processes involves chemical treatment, drying, and high-pressure hot pressing, sometimes for extended periods, sometimes with resin infiltration on top. A sawmill, by comparison, is a blade and a conveyor. Timber is one of the cheapest structural materials on Earth precisely because processing it is almost trivial. To compete on a construction site, where margins are counted in cents per board foot, densified bamboo has to survive a comparison not with a laboratory sample, but with the cheapest possible plank. Most of these processes have been demonstrated on relatively small specimens. Scaling a chemical and pressing operation up to the size of a floor joist, at the volumes a construction industry consumes, is a manufacturing problem that has not been fully solved in public. The second barrier is durability under real conditions, and this one is specific to the chemistry. Lignin, remember, is partly what makes a plant waterproof. If you deliberately remove some of it, you have to put that protection back some other way, through resins, coatings, mineralization, or surface treatment. Several of the published studies address exactly this, reporting water absorption and thickness swelling figures, precisely because everyone in the field knows it's the obvious question. A building material doesn't get judged on how it performs in a lab in month 1. It gets judged on how it performs in a damp wall cavity in year 30. That data, by definition, doesn't exist yet for materials invented in the last few years. The third barrier is the one almost nobody talks about, and it's the biggest. It's paperwork. Engineers cannot legally specify a material that doesn't have a code behind it. Timber has a century of standards, published design values, tested connection details, and accumulated failure data. Bamboo is only now getting there. The International Standard for Structural Bamboo Design, ISO 22256, was updated in 2021, and there are companion standards covering how to test bamboo's physical and mechanical properties and how to characterize glue-laminated and scrimber bamboo products. But according to a recent review of engineered bamboo for sustainable construction, ISO 22256 limits bamboo residential structures to 2 stories, or about 7 meters in height, specifically because there isn't enough fire performance data for anything larger. Not because bamboo failed a fire test, because the tests haven't been run at that scale yet. That gap is closing. In January 2026, researchers published what was described as the first structural engineering manual for designing bamboo buildings to the ISO 22556 standard, led by Dr. David Trujillo at the University of Warwick, with Professor Kent Harries at the University of Pittsburgh, in coordination with the International Bamboo and Rattan Organization. Reporting on that publication noted the same underlying issue. Without a unified framework for loads, connections, fire performance, moisture, and long-term durability, engineers simply default to steel, concrete, and engineered timber because those come with decades of documented performance. Codes don't reject new materials. They just have nothing to say about them, and silence is a rejection in practice. So the real bottleneck isn't the physics. The physics is published, peer-reviewed, and reproducible across multiple independent groups. The bottleneck is the unglamorous work of testing, standardizing, certifying, and ensuring, which takes years and generates no headlines whatsoever. Here's where this story gets bigger than a building material, though. Because what's happening in these labs isn't an isolated invention. It sits inside one of the largest deliberate material substitution programs any country has ever attempted. China has roughly 7 million hectares of bamboo forest, an area comparable in size to the entire island of Ireland, spread mostly across Zhejiang, Fujian, Jiangxi, Anhui, Hunan, Sichuan, and Guangdong. In late 2023, Chinese state bodies, including the National Development and Reform Commission and the Forestry Administration, issued a 3-year action plan to accelerate what they call bamboo as a substitute for plastic, laying out 6 objectives and 23 specific actions, launched alongside a global action plan running to 2030, developed with the International Bamboo and Rattan Organization. In September 2024, the Forestry Administration issued a dedicated standard system for bamboo plastic substitutes covering 9 product categories, including engineering and construction materials. By early 2026, the National Forestry and Grassland Administration reported that the country's bamboo industry had exceeded an annual output value of 520 billion yuan, with more than 15,000 product varieties, up from 82 billion yuan in 2010. There's also a historical irony buried in this. China has been working with bamboo for something in the order of 7,000 years for baskets, scaffolding, paper, tools, and houses. It was never an exotic material there. It was the ordinary one, the cheap one, the material you used when you couldn't afford timber. What's changed isn't the plant, it's that the processing technology finally caught up to what the plant was always capable of, and the cheap material got promoted. And it's worth noting that the same trick is being run on wood itself. The delignification and densification approach isn't bamboo specific, it's cellulose specific, and research groups have applied variations of it to ordinary timber and even to low-value wood waste, damaged, decayed, or discarded material, converting it into dense structural stock far stronger than the plank it started as, which reframes the whole question. This may not end up being a story about bamboo defeating wood at all. It may be a story about raw, unprocessed plant fiber of any species becoming the thing that's obsolete, replaced by engineered versions of the same molecule that we currently throw away as offcuts. And this is spreading into places that have nothing to do with furniture. Chinese firms have developed what's called bamboo winding composite technology, in which bamboo fiber is wound in continuous layers to form pipes and structural shells. According to reporting on the company that pioneered it in Zhejiang, this technique is being used for large-diameter pressure pipes, urban utility tunnels, and the firm's chairman has described applying it to rail carriage structures. The stated pitch is that these components are light, insulating, corrosion-resistant, and can substitute for materials with far higher embodied energy, like steel and cement. That's the part worth sitting with. The interesting story is not that somebody made a strong plank out of a grass. It's that a lot of separate efforts, academic labs chasing publication records, startups chasing patents, and a national industrial policy chasing plastic and steel substitution, have all independently converged on the same underlying insight. Cellulose, the most abundant structural polymer on the planet, has always been stronger than the plants that carry it. We were never limited by the fiber, we were limited by the packaging around it. And once you learn to take the packaging off and press the fibers together, the distinction between a fast-growing grass and a slow-growing hardwood starts to look less like a law of nature and more like a processing choice. None of which means the wood industry is ending. Let's be precise about this. Nothing in this video is a finished, code-approved, mass-produced product sitting on a shelf competing with pine. Timber is cheap, deeply embedded, well understood, and, when it comes from properly managed forests, genuinely renewable. The realistic near-term picture is not replacement, but encroachment. Bamboo-based materials, taking flooring first, then decking and paneling, then non-structural interiors, then eventually load-bearing elements in low-rise buildings where the codes already permit it, with each step needing its own decade of evidence. That's how material transitions actually happen, not with an announcement, but with a slow substitution nobody notices until it's already done. It's a strange thing to sit with, honestly. The plank in your floor and a laboratory sample of densified bamboo are made of essentially the same molecule, arranged by the same biological machinery, differing mainly in how tightly it's packed and what's been removed from around it. One took 80 years to grow, the other took 4. And the reason we still overwhelmingly use the 80-year version isn't that it's better, it's that we've had 80 years of practice trusting it, which leaves the question I'll hand back to you. Wood, cement, steel, and glass, the 4 materials almost every building you've ever entered is made of, were all effectively locked in before your grandparents were born. Somewhere right now, in a lab that will never make the news, somebody is quietly doing to one of the other 3 what these teams did to bamboo. Which one do you think falls first? Tell me in the comments. And if you want to keep finding the science hiding inside the most ordinary objects around you, subscribe, because that's exactly what we do here.